In 1987, astronomers witnessed the brightest supernova of the 20th century SN 1987A. A star's violent death lit up the skies and rewrote what we knew about the universe. What secrets did it reveal, and what mysteries remain? In this video, we'll explore the cosmic fireworks that stunned the world. If you enjoy it, please like, subscribe and share, and tell us in the comments, what would you ask a dying star if you could? Thank you for watching. Now, let's begin. In the southern sky lies a faint companion to the Milky Way, a small and irregular system known as the Large Magellanic Cloud. From Earth, it is visible to the naked eye as a smudge of light hanging low for those who observe from the southern hemisphere. This dwarf galaxy orbits the Milky Way at a distance of about 160,000 light-years, close enough for astronomers to resolve many of its individual stars. Its irregular form is shaped by gravitational interactions and the pull of its larger neighbour, giving it an asymmetric and scattered appearance. Within its expanse stretches a complex network of bright star-forming regions, dark dust lanes and open clusters, providing an ideal setting for the study of stellar evolution. The Large Magellanic Cloud has long been important for astronomers. Because it sits outside the Milky Way yet remains close, it offers a vantage point free from much of the obscuring dust that complicates studies within our own spiral arms. Its stars can be observed in clear relief, their distances relatively well constrained compared to those scattered across our galaxy. It is here that generations of telescopes have turned, seeking to understand how stars are born, evolve, and eventually die. Among the most prominent structures within this galaxy is the Tarantula Nebula, a vast region of active star formation. It glows brightly in hydrogen emission, revealing knots of hot gas where massive stars pour out radiation. The nebula is surrounded by clusters of luminous young stars, some exceeding many tens of times the mass of the Sun. These stellar giants have short lifespans, burning their fuel rapidly, and destined to end in violent supernova. The Large Magellanic Cloud as a whole has become a natural laboratory for studying such events, hosting numerous examples of stellar remnants. The chemical makeup of the Large Magellanic Cloud differs from that of the Milky Way. Its metallicity, the proportion of elements heavier than hydrogen and helium, is lower than that of the Sun. This difference means that stars within it evolve slightly differently from those in our galaxy, with consequences for their winds, temperatures, and lifetimes. Such variations provide astronomers with a comparison point, allowing them to refine models of stellar physics. The galaxy's proximity makes even faint features accessible to study, and so its population of massive stars has been catalogued extensively. When observing the Large Magellanic Cloud, astronomers are not simply gazing at individual stars. They're examining an entire galactic ecosystem where gas clouds collapse to form new stellar generations, where winds carve cavities in the interstellar medium, and where ancient supernovae leave behind filaments and shells of expanding debris. Across its face, the interplay of light and shadow reveals the cycle of birth and death. From hot blue giants to diffuse remnants, the stages of stellar existence are spread out for inspection. In the night sky, the Large Magellanic Cloud has played a role in navigation and cultural stories for peoples of the southern continents. For early astronomers, it became a reference point, a visible marker of the universe beyond the Milky Way. By the 20th century, it was recognized not merely as a cloud or nebula, but as a galaxy in its own right, distinct though bound to the gravitational pull of our own. Telescopic surveys mapped its features, and photographic plates captured the speckled richness of its stellar fields. As technology advanced, the Large Magellanic Cloud became a prime target for optical telescopes, radio arrays, and later space-based observatories. Each wavelength revealed new aspects. Radio maps traced the neutral hydrogen that pervades the galaxy. Ultraviolet images highlighted hot young stars, and infrared surveys uncovered cooler dust clouds and embedded stellar nurseries. Together, these views built a comprehensive picture of a galaxy both familiar and distinct. Within this environment, the conditions for massive star evolution are abundant. Dense star clusters such as R136 within the Tarantula Nebula harbor some of the most massive stars known, exceeding 100 times the mass of the Sun. Such stars burn furiously, exhausting their hydrogen fuel in only a few million years. Their eventual deaths in supernovae are not rare occurrences here, though the chance of observing one in real time remains exceptional. Throughout the 20th century, astronomers scanned this galaxy not only for its luminous stars but for the traces of past explosions. Supernova remnants, glowing shells of gas expanding from earlier events, dot its expanse. Some are centuries old, others many thousands of years, their debris fields mixing with the interstellar medium. These remnants provide evidence of the ongoing cycle of stellar death and rebirth within the galaxy. The Large Magellanic Cloud is also a place of motion and change. Its stars orbit within a gravitational potential disturbed by its interaction with both the Milky Way and the Small Magellanic Cloud. Streams of gas connect the systems, stretching across intergalactic space in long filaments. These tidal features are testimony to billions of years of orbital interplay. They bring in fresh material to fuel star formation and shape the long-term fate of the galaxies. For astronomers in the mid-20th century, the Large Magellanic Cloud held promise as a stage upon which one of the universe's most dramatic events might be witnessed. With so many massive stars concentrated in its regions, the likelihood of a supernova occurring was higher than in many other visible fields. Yet such explosions are still rare on human timescales separated by centuries or millennia. The possibility remained that generations could pass without a clear opportunity to see one with modern instruments. Nonetheless, patient observation continued. Photographic surveys catalogued its stellar population. Spectroscopic campaigns characterized its brightest stars. Observatories across the southern hemisphere pointed regularly toward its regions, gathering baseline data. In this context, the sudden appearance of a new star-like point of light would not go unnoticed. When a star in this galaxy finally did collapse, it would be the culmination of millions of years of evolution, its fate sealed by processes invisible until the final instant. The Large Magellanic Cloud provided the stage and human observers the watchful eyes waiting for a star to end its life in a blaze visible across intergalactic space. As the 20th century advanced and astronomical technology improved, detectors became more sensitive, and telescopes grew larger and more precise. The ability to monitor the Large Magellanic Cloud increased. By the 1970s and 80s, astronomers had access to arrays of instruments able to capture light across a wide range of wavelengths, from gamma rays to radio waves. This set the stage for one of the most important observational opportunities in modern astronomy. Though none could predict the exact star or the precise time, yet the galaxy's role as a nearby companion meant that when such an event occurred, it would be brighter than any other supernova recorded in centuries, offering data of unprecedented clarity. The Large Magellanic Cloud, in its modest span across the sky, was ready to reveal one of the defining astronomical events of the 20th century, though its coming remained unseen until the night it began. Within the Large Magellanic Cloud, the region where the future supernova would occur is not isolated but set within a bustling stellar neighborhood. This corner of the galaxy contains not only bright stars but also diffuse gas and dust remnants of prior generations of stellar activity. When viewed through telescopes, the field is dotted with luminous blue stars, and the faint glow of surrounding nebulosity. The interstellar medium here is active, stirred by winds from massive stars and shaped by earlier explosions. This environment creates a layered stage where the death of one star becomes part of an ongoing cosmic cycle. The interstellar medium in this region is composed of hydrogen, helium, and traces of heavier elements. Large molecular clouds are scattered across the area, some dense enough to collapse and give rise to new stars. Others are tenuous, forming a backdrop of diffuse material that interacts with radiation and stellar winds. These clouds absorb and scatter light, making them visible in silhouette against brighter backgrounds or as glowing emission nebulae when energized by ultraviolet radiation. This dynamic landscape is not static. Winds from massive stars push against surrounding gas-carving cavities and driving shock fronts outward. These winds, streaming at thousands of kilometers per second, compress nearby material and influence the formation of subsequent generations of stars. In the immediate vicinity of the progenitor star of SN 1987A, these processes had been shaping the interstellar environment for millions of years. The concentration of massive stars nearby was not coincidental. Regions like this arise when large molecular clouds collapse, fragment, and form clusters of stars of various masses. While many stars in such regions are small and long-lived, the massive stars dominate the luminosity and inject large amounts of energy into their surroundings. Their radiation ionizes hydrogen gas, creating glowing H2 regions. Their winds sculpt the medium into arcs and bubbles visible as curved outlines against the starlit sky. It is within one of these star-forming regions that Sanduleak 69202, the progenitor of SN 1987A, resided. Observations before the supernova showed that the region contained numerous blue stars, many of them young and massive. The presence of these hot stars gave the field a characteristic appearance rich in ultraviolet radiation and energetic winds. This environment was not simply a backdrop, but a critical influence on the star's evolution, shaping its mass loss, surface temperature, and eventual collapse. When astronomers study the interstellar medium around SN 1987A, they find signatures of both ancient and recent activity. Some filaments of gas are remnants of earlier supernovae, their shock-heated material continuing to expand outward. Others are shells of gas created by winds from massive stars layered like concentric bubbles around their sources. Still others are regions of active star formation, where dense knots of gas are giving birth to new stars even as their massive neighbours approach the ends of their lives. The interplay of these elements creates a tapestry of energy and matter that defines the stellar neighbourhood. The radiation field in this region is particularly strong. Ultraviolet light from massive stars ionizes nearby hydrogen, producing bright emission lines that dominate the spectra of surrounding nebulae. The ionization fronts, where neutral hydrogen becomes ionized, move steadily through the gas, leaving behind glowing shells and pillars. Such features reveal the presence of hot young stars and indicate the transformative effect they have on their environment. Against this luminous backdrop, Sanduleak 69202 blended into a population of similar stars, though its fate would soon distinguish it in history. Dust is another key component of this stellar neighbourhood. Microscopic grains of carbon, silicates, and other compounds are mixed with the gas, altering the way light passes through the region. Dust absorbs ultraviolet and visible radiation, re-emitting it in the infrared. This process obscures some stars while highlighting warm dust clouds when observed at longer wavelengths. The balance of gas and dust influences both the formation of new stars and the appearance of the region as a whole. The area around the progenitor was neither empty nor uniform, but filled with this complex medium that would later interact with the shock waves of the supernova. The motions of stars within this neighborhood also contribute to its complexity. Clusters of massive stars often drift apart as gravitational interactions alter their trajectories. Some stars are ejected at high velocities, becoming runaways that travel far from their birthplace. Others remain in loose associations, their collective radiation shaping the clouds around them. Over time, the cumulative effect of these motions is a constantly changing pattern of illumination and shadow across the region. Astronomers examining archival images of the Large Magellanic Cloud before 1987 find a crowded field of stars near the eventual site of the supernova, with no clear indication that one of them was on the verge of catastrophe. The neighborhood also contained evidence of past cataclysms. Supernova remnants from earlier events lie scattered across the galaxy, and some are relatively close to the site of SN 1987A. These remnants, with their filamentary shells and glowing arcs, testify to the inevitability of stellar death in regions where massive stars are common. The presence of such remnants underscores that the environment was already enriched by earlier generations of stars. Elements heavier than helium forged in those explosions had mixed with the interstellar medium, altering the chemistry of subsequent stars. This chemical enrichment is central to the evolution of galaxies. Each supernova injects heavy elements such as oxygen, silicon, and iron into the surrounding gas. These elements become part of future stars and planets. In the case of the Large Magellanic Cloud, with its lower initial metallicity, each successive cycle of star birth and death has gradually increased the abundance of heavy elements. By the time Sandolik 69202 reached the end of its life, the interstellar medium around it had already been transformed by previous stellar generations. The interplay of gas, dust, radiation, winds, and remnants defines the local stellar neighborhood in which SN 1987A occurred. This environment ensured that when the supernova happened, it would not simply be an isolated event, but one embedded in a broader tapestry of galactic evolution. The shock waves, radiation, and debris from the explosion would soon interact with this medium, leaving signatures that could be studied for decades. Before the event, however, this neighborhood appeared as another rich field of stars and nebulae, remarkable, but not yet historic. Astronomers could catalogue its stars, measure their spectra, and map the glowing gas, but the true transformation would not come until one of its massive members collapsed. The significance of the stellar neighborhood lies not only in its influence on the progenitor star, but also in the way it allowed astronomers to observe the supernova against a detailed and well-characterized background. The surrounding stars provided reference points for measuring brightness changes. The gas and dust offered a medium through which the expanding shock waves could be traced. The entire environment functioned as a natural laboratory, amplifying the insights gained from the explosion. In the quiet years before 1987, the neighborhood remained steady, its stars shining as they had for millennia. Observations taken during this period would later prove invaluable, providing a baseline for comparison after the supernova. With this data, astronomers could distinguish changes due directly to the event from the pre-existing structures of the region. In this way, the stellar neighborhood of SN 1987A stands as more than scenery. It is a key part of the story, a framework within which one of the most important astronomical events of the 20th century unfolded, linking a single star's death to the larger processes shaping a galaxy. Among the many bright stars scattered across the Large Magellanic Cloud, one in particular drew only passing notice before the year 1987. It carried the catalogue name Sandolik 69202, often abbreviated in the astronomical records of the time. This designation came from a survey conducted by Nicholas Sandolik in the 1970s, in which he catalogued hot blue stars within the Magellanic Clouds. To most observers, it was just another entry among thousands, shining steadily with no obvious sign that it was poised on the brink of catastrophe. The star was classified as a blue supergiant with an estimated mass more than 20 times that of the Sun. Its surface temperature exceeded 10,000 degrees Celsius, giving it a bright blue hue. Such stars are rare and short, spending only a few million years on the main sequence before exhausting the hydrogen fuel in their cores. The sheer mass of Sanduleak-69202 meant that its fate was sealed from the moment of its birth. Unlike smaller stars which end quietly as white dwarfs, this one would end in a supernova. Before the explosion, the star's properties were studied with modest interest by astronomers. Photographic plates captured its brightness, placing it at a magnitude faint enough to require careful observation, but bright enough to be included in catalogues. Spectroscopic data suggested that it was indeed a massive star, but there was little to distinguish it from its neighbours. It did not exhibit the strong emission lines associated with unstable stars or the rapid variability of eruptive variables. In the years before 1987, Sanduleak-69202 sat quietly, a luminous but unremarkable star in the southern sky. Its apparent ordinariness highlights the challenges astronomers face when trying to predict which massive stars will explode and when. While theoretical models provide timescales for the lives of such stars, the precise moment of collapse remains hidden. The outer layers of a star can appear stable even as the core undergoes dramatic changes. Sanduleak-69202 gave no outward sign of its imminent demise, a reminder that the end of a star can come suddenly with little warning for those observing from afar. As a blue supergiant, the star occupied an unusual position in the taxonomy of stellar evolution. Many models at the time suggested that massive stars should end their lives as red supergiants with cooler surfaces and extended outer envelopes. The fact that Sanduleak-69202 was still a hot compact blue star raised questions even before its explosion. Some astronomers speculated that stars in the low metallicity environment of the Large Magellanic Cloud might evolve differently, losing less mass through winds and retaining more compact structures. The significance of this would only become clear after the supernova, but even in archival data the peculiarity of the progenitor's spectral type stood out. The surrounding cluster of stars also provides context. Sanduleak-69202 was part of an association of young massive stars that had formed from the same molecular cloud. Their ages were measured in only a few million years, a blink on the timescale of stellar evolution. Within this group, stars of varying masses followed different evolutionary tracks, some remaining on the main sequence, others swelling into red supergiants, and still others progressing into luminous blue variables. Sanduleak-69202, by all appearances, had remained a stable blue supergiant, and it was in this state that it finally collapsed. Photographs taken by observatories in Chile and Australia during the 1970s and early 1980s preserve the image of the star before its explosion. These archival images later became vital for identifying the progenitor. After the supernova, astronomers combed through past plates to confirm that the bright new object had indeed appeared in the position of Sanduleak-69202. The comparison made clear that the progenitor had vanished, replaced by the expanding cloud of the explosion. The nature of this star speaks to the diversity of massive star evolution. While red supergiants such as Betelgeuse in the Milky Way are often cited as typical progenitors of core collapse supernovae, blue supergiants represent a rarer but significant pathway. The conditions that led Sanderleak -69202 to remain blue rather than evolving into a cooler giant may involve subtle balances of mass metallicity and rotational dynamics. These factors influence how stars lose mass through stellar winds, how their internal layers mix, and how quickly they burn through successive stages of nuclear fuel. At the time, astronomers did not have detailed space-based imagery of the star. The Hubble Space Telescope had not yet been launched, and ground-based observatories faced the limitations of atmospheric turbulence. Still, the data available were sufficient to establish its identity. When the supernova occurred, the fact that the progenitor had been catalogued at all was a stroke of fortune. Many other supernovae observed in distant galaxies lack a confirmed progenitor star because pre-explosion images are either absent or too faint. The presence of Sanderleak -69202 in archival surveys made SN 1987A one of the best documented supernovae in history. The mass of the progenitor determined its destiny. A star with 20 solar masses generates immense pressures and temperatures in its core sufficient to fuse not only hydrogen and helium, but progressively heavier elements up to iron. Each stage of fusion occurs more rapidly than the last, with the late burning phases lasting mere years or months. By the time Sanderleak -69202 reached the end of its life, its core was composed largely of iron, unable to release energy through further fusion. When the collapse came, it was swift and catastrophic. Yet before that night in February 1987, nothing in its outward appearance revealed this looming fate. Its steady blue light travelled across 160,000 light-years of intergalactic space, reaching Earth, as it had for millennia unnoticed except by careful cataloguers. To the unaided eye, the progenitor was invisible, too faint to stand out in the crowded southern sky. Only with telescopes could it be identified and recorded. In the years to come, its quiet presence in the archives would become the foundation for an unparalleled scientific investigation. Sanderleak -69202 thus represents not just a star, but a turning point in our understanding of stellar death. Its explosion as SN 1987A revealed that blue supergiants could indeed collapse challenging assumptions and reshaping models. But before that moment, it was simply another luminous entry in a catalogue, awaiting the instant when it would shift from obscurity to prominence. Its life spanned millions of years, but for astronomers its significance began in earnest only when the core finally failed. The quiet record of its pre-supernova existence remains a reminder of the hidden dramas that unfold within stars unseen, until the final eruption of light. The life of a massive star like Sanderleak -69202 follows a path of extraordinary intensity. From the moment of its birth in a dense molecular cloud within the Large Magellanic Cloud, it carried within it the seeds of its own destruction. Its mass, more than 20 times that of the Sun, determined that it would burn its fuel at a prodigious rate, racing through stages of nuclear fusion that smaller stars consume leisurely over billions of years. The star's core initially fused hydrogen into helium, a process that produces the energy that counterbalances the inward pull of gravity. For millions of years, this balance maintained its stability. The outer layers shone brightly, radiating blue-white light into space, while the inner furnace quietly converted hydrogen at temperatures of millions of degrees Celsius. Yet, as with all massive stars, hydrogen in the core was eventually exhausted. When this occurred, the delicate balance began to shift. With no more hydrogen fusion at its center, the core contracted under gravity, raising its temperature and pressure to levels sufficient to ignite the next fuel, helium. In this phase, helium atoms fused into carbon and oxygen, releasing energy and halting the collapse for a time. The star adjusted to a new equilibrium, burning more fiercely than before. Surrounding layers continued to burn hydrogen in shells around the core, feeding material inward. The star's structure grew more complex, with multiple shells of different fusion processes layered like the rings of an onion. Each stage of fusion happened more quickly than the last. While hydrogen fusion had lasted for millions of years, helium burning persisted for only a fraction of that time. As carbon accumulated in the core, the cycle repeated. Once helium was depleted, the core contracted again, temperatures rose, and carbon burning began producing heavier elements such as neon sodium and magnesium. The process accelerated with each successive stage of burning shorter than the last. Oxygen fusion followed, then silicon burning, each lasting mere years or months. During these final stages, the star's core was undergoing transformations invisible to outside observers. On the surface, Sanderleak -69202 continued to shine with steady blue light. Its luminosity and temperature gave no clear indication of the turmoil beneath. But within a cascade of nuclear processes was building toward an inevitable end. The creation of iron in the core marked the final stage of this journey. Unlike lighter elements, iron cannot release energy through fusion. When the core became dominated by iron, no further fuel was available to support the star against collapse. At this point, gravity gained the upper hand. The core contracted catastrophically, and the outer layers were destined to fall inward in a chain reaction that would culminate in a supernova. Before the final collapse, the star had already shed material through stellar winds. Although the Large Magellanic Cloud's lower metallicity reduced the strength of these winds compared to stars in the Milky Way, they still carried away significant mass, creating a circumstellar environment rich in gas and dust. Observations of the region revealed faint nebulosity evidence that the progenitor had lost material into space long before the explosion. These outflows would later play a critical role in shaping the structures illuminated by the supernova. The peculiar fact that Sanderleak -69202 ended its life as a blue supergiant rather than transitioning into a red supergiant puzzled astronomers. In stellar models, massive stars often swell dramatically in their final phases, their outer layers expanding and cooling to form enormous red supergiants. Yet in this case, the star remained hot and compact. Several possibilities were considered, including the influence of rotation differences in mass loss rates, or the effects of binary interaction if a companion star had once been present. Whatever the cause, the fact that the progenitor remained a blue supergiant added an additional layer of complexity to its story. For astronomers studying massive stars, this was not only a curiosity, but a clue that stellar evolution could take multiple paths depending on environment and initial conditions. The late stages of nuclear fusion inside the star created layers rich in different elements. In one shell, hydrogen still burned into helium. Deeper within helium fused into carbon. Still deeper carbon transformed into neon and oxygen. And in the innermost regions, silicon fused into iron. The star resembled a vast layered furnace, each stage proceeding with ferocious intensity. These processes seeded the elements that would later be dispersed into space. Oxygen, magnesium, silicon, and calcium materials that would one day be part of planets and life were being forged in the final moments of the star's existence. Yet none of these developments could be seen by astronomers before 1987. From Earth, Sanderleak -69202 appeared unchanged, a faint blue point of light catalogued and then overlooked. Only theoretical understanding of stellar evolution hinted at the reality unfolding within. The end came when the iron core reached a critical mass. At that instant, the inward pull of gravity crushed it beyond the point where pressure from electrons could resist. The collapse accelerated, occurring in less than a second. Protons and electrons were forced together, creating neutrons and releasing a flood of neutrinos, ghost-like particles that streamed outward in unimaginable numbers. The core, now composed of neutrons, halted its collapse only when densities comparable to those of atomic nuclei were reached. The rebound of this collapse launched a shockwave outward through the star, tearing its outer layers apart. The entire sequence was set in motion by processes that had been building for millions of years, but culminated in a sudden and catastrophic moment. For Earthbound observers, the prelude to this collapse was invisible. The star shone as it always had, its light crossing 160,000 light-years of intergalactic space. But on the night of February 23, 1987, that light was joined by a brilliant surge from the explosion, announcing to the universe that Sanderleak -69202 had reached its end. The evolutionary journey of the progenitor star is central to understanding why SN 1987A was so extraordinary. The interplay of nuclear burning mass loss and environmental factors shaped not only the star's life, but also the character of its death. The layers it created inside would dictate the composition of the ejector. The winds it drove earlier would form the structures into which the shockwave would expand. Its unusual identity as a blue supergiant would challenge established theories and force astronomers to reconsider how massive stars live and die. In the quiet years before its collapse, all of this remained hidden, locked inside the blazing furnace of Sanderleak -69202. Yet when the core failed, the results would become visible across the cosmos, transforming a once obscure star into the brightest and most studied supernova of the 20th century. On the night of February 23, 1987, astronomers in the southern hemisphere began to notice a new point of light in the sky. It appeared in the constellation Dorado, within the familiar bounds of the Large Magellanic Cloud. At first, it resembled a bright star, one that had not been visible before. For observers accustomed to the region, its sudden presence was unmistakable. The discovery is often credited to Ian Shelton, working at the Las Campanas Observatory in Chile, who noticed the new object on photographic plates. Within hours, confirmation came from other observatories and even from amateur astronomers with small telescopes. The event quickly became known as Supernova 1987A, marking it as the first supernova of that year, and soon to be recognized as the most significant in centuries. The brightness of the object was remarkable. Supernova had been recorded before, but most occurred in distant galaxies and required telescopes to study. This one, however, was visible to the naked eye, reaching a peak brightness, comparable to some of the brightest stars in the night sky. For the first time since the invention of modern instruments, astronomers could study a supernova in detail as it unfolded in real time. The proximity of the Large Magellanic Cloud, only 160,000 light-years away, meant that the light from the explosion was both intense and accessible to every type of telescope then in operation. The timing was also fortuitous. By the late 1980s, observatories across the world had access to a wide range of instruments, from ground-based optical telescopes to radio arrays and early space-based observatories. The global network of astronomers could coordinate observations across wavelengths, capturing a comprehensive picture of the event. Within days, the supernova was being monitored around the clock as researchers sought to document every stage of its evolution. The discovery sparked excitement not only among professional astronomers, but also among the public. Newspapers reported the sudden appearance of a new star, echoing descriptions from historical times when supernovae had been observed without understanding. Yet unlike those earlier events, this one unfolded under the gaze of modern science. data could be recorded with precision spectra, analysed for composition, and images archived for long-term study. For many, it represented a unique chance to witness the death of a star with clarity unmatched in human history. The observational circumstances of the discovery highlight the role of both technology and vigilance. Photographic plates, long the standard for capturing the sky, provided the first evidence. In these plates, the new object appeared as a bright dot against the familiar star field. Subsequent visual confirmation came from direct observation, through telescopes where the brightness was striking enough to be seen immediately. Amateur astronomers in New Zealand and Australia also spotted the new light, underscoring how unusual and brilliant it was. The designation 1987A reflected the established naming system for supernovae. Each year, the first discovered event receives the letter A, the second B, and so on. That this one occurred early in the year added to the sense of immediacy, as astronomers had barely begun their observational campaigns when it appeared. By the time reports spread globally, the supernova was already being tracked by instruments designed to monitor variable stars and transient phenomena. In the first hours and days after its discovery, astronomers noted its rapid rise in brightness. The light curve record of brightness over time showed a sharp increase as the explosion expanded and the outer layers of the star radiated immense energy. Even with the naked eye, the change was visible from night to night. For professional observers, this was a rare opportunity to trace the unfolding of a stellar explosion in unprecedented detail. The discovery of SN 1987A was not a single moment, but a sequence of confirmations. Initial photographic evidence was quickly supplemented by direct viewing, followed by spectral analysis that confirmed the nature of the event. The spectra showed broad absorption and emission lines, signatures of high-velocity gas expanding outward. The chemical fingerprints revealed the presence of hydrogen, indicating that the progenitor had retained much of its outer envelope before the collapse. This was a crucial clue linking the event back to the peculiar identity of Sanduleak -69202 as a blue supergiant. The location of the supernova within the Large Magellanic Cloud also aided astronomers. Unlike supernovae in distant galaxies, whose precise distances can be difficult to determine, the distance to the Large Magellanic Cloud was relatively well established. This allowed for accurate calibration of the energy output. By comparing observed brightness with known distance, astronomers could calculate the luminosity and refine models of the explosion. The proximity also meant that the event could be studied across the electromagnetic spectrum with high resolution. From the moment of discovery, observatories coordinated observations. Optical telescopes charted the changing brightness. Infrared instruments traced the heating of surrounding dust. Radio telescopes monitored emissions from high-energy electrons spiraling in magnetic fields. Space-based detectors recorded ultraviolet and gamma-ray signals. Each wavelength provided a different piece of the puzzle together, forming a complete picture of the supernova's unfolding. The discovery of SN 1987A was also remarkable because of its timing with respect to neutrino observatories. Just hours before the visible light reached Earth underground detectors in Japan, the United States and Russia recorded a burst of neutrinos confirming theoretical predictions about the core collapse process. Although these detections will be discussed in greater detail later, their coincidence with the discovery of the supernova provided immediate evidence that the explosion involved the catastrophic collapse of a massive star's core. For the scientific community, the chance to study such an event in such proximity was unprecedented. Supernovae are rare, occurring only once or twice per century in a galaxy the size of the Milky Way. To have one occur in the nearby Large Magellanic Cloud within reach of detailed study was an extraordinary stroke of luck. It was the first naked-eye supernova since Kepler's supernova of 1604, and the first to be studied with modern instruments. The circumstances of its discovery cemented its place as one of the most important astronomical events of the 20th century. As the days turned to weeks, SN 1987A continued to brighten, drawing global attention. From observatories high in the Chilean Andes to small backyard telescopes in suburban neighborhoods, the new star was watched and recorded. For professional astronomers, it marked the beginning of a long campaign of observations that continues to this day. For the public, it was a reminder that the universe remains dynamic, capable of sudden displays of power and light. The discovery in February 1987 thus represents the moment when a star's long-hidden fate became visible. From the quiet catalogue entry of Sandelik-69202, the sky was transformed into a sight of brilliance and wonder. In the weeks that followed, astronomers would record the details of its light curve spectra and shock waves, building a scientific record of unparalleled depth. But it all began with the sudden recognition of a new point of light in the southern sky, brighter than any supernova of the modern era. The first nights after the discovery of SN 1987A revealed the extraordinary brightness of the new object, and allowed astronomers to construct one of the most detailed light curves ever recorded for a supernova. A light curve traces how the brightness of an astronomical event changes over time, and in this case the progression was carefully measured across visible, ultraviolet and infrared wavelengths. Initially, the supernova brightened rapidly. Within hours of discovery, it was clear that the object was increasing in luminosity at a pace that matched expectations for the explosive ejection of stellar material into space. For several days, the brightness continued to rise, reaching a maximum around magnitude 3, visible to the unaided eye under dark skies. To many, this resembled a new bright star within the familiar patterns of the southern constellations. Unlike stars, however, its brightness was not steady. The rise and decline followed the predictable path of a stellar explosion radiating energy from deep within. The detailed tracking of this light curve was possible because the supernova was bright enough to be observed with a wide range of instruments. Small telescopes could contribute measurements, while larger observatories recorded precise data across multiple bands of light. This collaboration between professional and amateur astronomers ensured nearly continuous monitoring, providing an exceptionally complete record. The shape of the light curve carried important clues about the physics of the explosion. In the first days, the luminosity was driven primarily by the shock-heated outer layers of the star. As the shock wave from the collapsing core tore through the envelope, it caused the outer material to glow intensely. This produced a sharp initial rise. After the peak, the brightness began to decline, but not in a simple way. The decline was influenced by radioactive decay of isotopes created in the explosion. Chief among these was nickel-56, an unstable isotope produced in large quantities during the supernova. As nickel-56 decayed into cobalt-56 and then into iron, 56, it released gamma rays and positrons. These particles deposited energy into the expanding ejector, causing it to remain luminous for weeks and months. The rate of decline in the light curve matched the decay times of these isotopes, confirming theoretical models of how radioactive decay powers the light of supernova after the initial flash. Observations in different wavelengths revealed further details. In the ultraviolet, the supernova shone brightly in the early days, gradually declining as the ejector expanded and cooled. In the infrared, measurements showed how dust and gas absorbed and re-radiated energy, tracing the thermal evolution of the debris. Together, these datasets allowed astronomers to model the physical conditions within the expanding shell. The light curve also showed irregularities that provided hints of the structure of the progenitor star. Unlike some supernovae that display smooth uniform declines, SN 1987A exhibited variations that suggested asymmetries in the explosion. These could have been caused by uneven mixing of elements in the ejector or by the geometry of the progenitor's outer layers. Such details became clearer as spectra were analysed, but even the raw brightness measurements indicated that the event was not perfectly spherical. The peak brightness of SN 1987A was less than that of some other historical supernovae, yet its proximity made it appear striking in Earth's skies. Its apparent magnitude was lower than that of the great supernova of the 16th and 17th centuries, yet because astronomers could measure it with modern tools, the scientific value was far greater. The absolute luminosity corrected for distance provided key data for calibrating models of core collapse explosions. One of the important aspects of the light curve was its timescale. The rise to peak brightness took a few days, followed by a decline that stretched over weeks. By comparing these timescales with theoretical predictions, astronomers could infer the size and structure of the progenitor star. The relatively fast rise and decline were consistent with the compact nature of a blue supergiant rather than the more extended envelope of a red supergiant. This confirmed the identity of Sanduleak 69202 as the progenitor and underscored the unusual nature of the event. As weeks passed, the light curve transitioned from being powered by shock heating to being sustained by radioactive decay. This phase provided one of the clearest demonstrations of how freshly synthesized elements can power the glow of a supernova. By measuring the decline rate, astronomers could estimate the total mass of nickel, 56, produced in the explosion. In the case of SN 1987A, the amount was about half the mass of the Sun, a significant yield that would later enrich the surrounding interstellar medium with heavy elements. The precision of the light curve measurements was enhanced by the widespread interest in the event. Observatories around the world coordinated their observations, ensuring that gaps caused by day or weather in one location were filled by others elsewhere. This continuous record captured subtle fluctuations that might otherwise have been missed. The collaboration set a precedent for the study of future transient events, demonstrating the value of global cooperation in astronomy. The light curve was also tracked in polarimetric measurements, which examine the polarization of light. These observations revealed small but significant asymmetries in the way light was emitted, providing further evidence that the explosion was not perfectly spherical. Such findings challenged earlier assumptions of symmetry in supernova models and indicated that complex dynamics were at play in the collapsing core. For many astronomers, the unfolding light curve of SN 1987A was more than data. It was the chance to watch theory become reality. Predictions about radioactive decay powering supernova light, about the timescales of brightening and fading, and about the role of nickel-56 were confirmed in real time. Each night's observations added new points to the curve, extending the record of one of the most extraordinary astronomical events of the modern era. As the months passed, the supernova dimmed, but it did not fade from scientific attention. The tail of the light curve continued to be monitored, stretching into years as the radioactive isotopes completed their decay chains. Even at faint levels, the residual glow carried information about the composition and structure of the ejector. These long-term observations provided insights into the cooling processes and the eventual formation of molecules and dust within the expanding shell. For the broader scientific community, the light curve of SN 1987A became a benchmark. It was studied not only as a record of a single event, but as a template for understanding supernova in general. Models of light emission, radioactive decay, and ejector dynamics were all tested and refined against its data. The lessons learned extended beyond this one explosion, influencing how astronomers interpret more distant and less well-documented supernovae. The brilliance of SN 1987A captured in its light curve was a rare gift. For the first time, a stellar explosion could be followed from its first appearance through its decline with continuous detailed observations. The curve traced not only the fading glow of a dying star but also the rise of a new era in astrophysics, where theory and observation met in a singular event of clarity and importance. As soon as the discovery of SN 1987A was confirmed, astronomers began to focus not only on its brightness, but also on its spectra. Spectroscopy, the analysis of light spread into its component wavelengths, provides one of the most direct windows into the physical processes of a supernova. By examining the patterns of absorption and emission lines, researchers can determine the composition temperature and velocity of the expanding ejecta. In the case of SN 1987A, the spectra revealed a wealth of information from the earliest days onward. The first spectra obtained within hours of discovery showed broad absorption lines that indicated rapidly expanding material. Hydrogen lines were especially prominent, confirming that the progenitor star had retained its hydrogen envelope at the time of collapse. This was significant because many models predicted that massive stars might lose much of their outer hydrogen through winds or binary interactions before exploding. The presence of strong hydrogen lines set SN 1987A apart from hydrogen-poor events such as Type Ib and Type Ike supernovae. It was classified as a Type II supernova, characterized by hydrogen features in its spectra. As the days progressed, the spectra evolved. The absorption lines broadened, showing that gas was moving outward at thousands of kilometers per second. These velocities were derived from the Doppler shifts of the lines, with some material measured at speeds exceeding 20,000 kilometers per second. The enormous kinetic energy implied by these motions underscored the violence of the explosion. Alongside hydrogen, other elements soon appeared. Helium, oxygen, calcium, and iron were detected, each with distinct signatures in the optical and ultraviolet spectra. These elements had been forged in the star's core or in the explosion itself, now hurled outward to become part of the interstellar medium. Their presence confirmed the role of supernovae as sources of the heavy elements that enrich galaxies and seed future generations of stars and planets. Spectra taken in the ultraviolet provided additional detail, though they required space-based observatories to avoid absorption by Earth's atmosphere. The International Ultraviolet Explorer satellite captured lines from highly ionized species, revealing temperatures of tens of thousands of degrees in the expanding shell. These observations helped astronomers map the conditions of the ejecta as they changed from the initial shock-heated state to the cooler, more diffuse phases that followed. Infrared spectra were also gathered, tracing the cooling gas and providing evidence for the formation of molecules in the ejecta. Carbon monoxide, one of the first molecules to form, was detected as the gas cooled below critical temperatures. These molecules hinted at the later formation of dust grains, an important process in the chemical evolution of galaxies. In the optical range, the H-alpha line of hydrogen became one of the defining features of SN 1987A's spectra. This strong emission line, formed by transitions in hydrogen atoms, grew prominent as the ejecta expanded and thinned. Its width and shape provided direct measures of velocity and geometry. Over time, changes in the H-alpha profile revealed asymmetry, suggesting that the explosion had not been perfectly spherical. These asymmetries supported the idea that core collapse supernovae involve complex dynamics, with jets, or clumps of material moving at different speeds and directions. Spectroscopy also allowed astronomers to estimate the mass of radioactive nickel, 56 synthesized in the explosion. The gamma rays released by the decay chain of nickel to cobalt and then iron interacted with the surrounding gas, producing emission lines that could be measured. By modelling these lines, astronomers estimated that about half a solar mass of nickel had been produced. This matched the requirements of the light curve and provided a consistent picture of how radioactive decay powered the supernova's glow. The spectra recorded in the first months after the explosion were only the beginning. As the years progressed, the ejector expanded and cooled and new features appeared. Forbidden lines produced under low-density conditions where atoms can undergo rare transitions became more prominent. These lines provided information about the densities and temperatures in the expanding gas. Oxygen in particular produced strong forbidden lines that revealed the distribution of heavier elements created in the star. High-resolution spectra taken with large telescopes revealed fine details, including small shifts that traced the motions of clumps within the ejector. These observations showed that the explosion was not uniform but patchy, with some regions richer in certain elements than others. This mixing of elements was evidence of turbulent processes during the collapse and explosion, in which the layers of the star were stirred and reshaped by shock waves. The presence of such mixing explained why elements formed deep in the core could appear at the surface soon after the explosion. Beyond composition and velocity, spectra also provided clues about the geometry of the explosion. The broad and sometimes asymmetric line profiles indicated that the ejector were not expanding as a perfect sphere but had irregular structures. This was consistent with polarimetric observations of light polarization, which also suggested departures from symmetry. Together, these findings implied that the collapse of Sanderleak -69202 and the subsequent explosion involved directional flows of matter, possibly jets or lobes, rather than a simple radial expansion. The rich spectral record of SN 1987A made it a benchmark for supernova research. Each set of lines traced a different aspect of the event, from hydrogen envelope retention to radioactive decay and molecular formation. For theorists, these data provided critical tests of models, allowing them to refine simulations of core collapse and explosion mechanisms. For observers, the spectra offered a continuous thread of information, evolving over days, months, and years, linking the moment of discovery to the long-term fate of the remnant. In the broader context of astronomy, the spectra of SN 1987A underscored the role of supernovae as cosmic forges. The detection of elements heavier than helium in the ejector confirmed that such explosions are key sources of the materials that build planets and life. Each spectral line was not just a signature of atomic transitions, but a marker of the universe's ongoing process of chemical enrichment. The study of SN 1987A's spectra continues even decades later. Modern instruments, including those aboard the Hubble Space Telescope and large ground-based observatories, still record the faint emissions from its ejector and surrounding rings. These later spectra reveal the ongoing interaction between the supernova's debris and its environment, but their foundation lies in the remarkable sequence of observations that began within hours of its appearance. The first spectra of SN 1987A remain among the most valuable ever obtained in astrophysics. They captured a stellar death as it happened, transforming the faint light of a once obscure blue supergiant into a detailed record of nuclear processes, shock dynamics, and elemental creation. Through them, astronomers gained not only insights into one star's end, but also a deeper understanding of the mechanisms that shape galaxies and the cosmos itself. Even before the brilliant light of SN 1987A reached Earth, another signal from the dying star had already arrived. Deep underground in Japan, in the United States, and in Russia, neutrino detectors registered sudden bursts of activity. Neutrinos are elusive particles with almost no mass and no electric charge. They pass through matter almost without interaction, making them extremely difficult to detect. Yet when a massive star's core collapses, the process releases a torrent of neutrinos, carrying away most of the energy of the explosion. For decades, theorists had predicted that a supernova would be accompanied by a neutrino burst, but never before had this been observed. On February 23, 1987, detectors around the world recorded the first direct evidence of this phenomenon. In Japan, the Kamiokande 2 detector, located in a mine beneath Mount Ikaneyama, registered a sequence of events lasting only seconds. 11 neutrinos were detected, far more than the normal background rate. In the United States, the Irvine, Michigan Brookhaven detector recorded 8 events, while in Russia, the Baksan Neutrino Observatory registered 5. Altogether, fewer than 30 neutrinos were seen, yet this tiny number carried immense significance. These detections occurred just hours before astronomers noticed the new point of light in the Large Magellanic Cloud. The timing was crucial. Neutrinos travelling nearly at the speed of light escaped the collapsing core almost immediately. Visible light, however, was delayed because it had to fight its way through the outer layers of the star, taking hours to emerge. The coincidence of the neutrino detections with the subsequent appearance of SN 1987A confirmed the theoretical link between core collapse and neutrino emission. The physics of this process is stark. As the iron core of the progenitor star collapsed, electrons and protons were forced together to form neutrons. This transformation released an enormous number of neutrinos. Within a few seconds, approximately 10 to the 58th power neutrinos streamed outward, carrying away the bulk of the gravitational energy released by the collapse. Only a vanishingly small fraction of these particles interacted with matter on Earth, yet the detectors captured enough to confirm the predictions. The significance of the neutrino detections extended far beyond mere confirmation. They provided the first direct observational evidence of what happens inside a star at the moment of core collapse, a process otherwise hidden from view. The energy's arrival times and numbers of neutrinos matched expectations from models, giving confidence that astrophysicists understood the basic mechanics of supernova explosions. At the same time, the data revealed new questions. The arrival times showed that the neutrinos were not emitted in a single instant, but over a span of several seconds. This indicated that the collapse and rebound of the core, along with the subsequent shockwave formation, was a process with structure rather than a single sudden event. The energies of the neutrinos also suggested that conditions in the collapsing core reached extraordinary extremes, with temperatures exceeding tens of billions of degrees Celsius. For the detectors themselves, SN 1987A was a landmark. The facilities had been built partly to study solar neutrinos and particle physics phenomena, not necessarily with the expectation of recording a galactic supernova during their operational lifetime. That such a nearby explosion occurred and produced a detectable signal was a rare stroke of fortune. It validated the investment in underground neutrino observatories and spurred the expansion of the field of neutrino astrophysics. The modest number of events recorded underscored just how challenging neutrino detection is. Trillions of neutrinos pass through every square centimetre of Earth every second, yet interactions are so rare that enormous volumes of water or heavy water are required to capture even a handful. That fewer than 30 neutrinos could provide such profound insights illustrates their power as messengers from the core of stars. The global distribution of the detectors added weight to the results. Independent facilities on 3 continents using different designs and methods all recorded signals at nearly the same time. This eliminated the possibility of local interference or background fluctuations. The consistency across sites gave astronomers and physicists confidence that they had indeed witnessed the neutrino burst from a supernova. The timing of the neutrino detections relative to the visible appearance of the supernova also allowed astronomers to refine their understanding of the delay between core collapse and breakout of light. This delay, measured in hours, provided constraints on the structure of the progenitor star's outer layers. In the case of Sanduleak -69202, the compact nature of a blue supergiant meant that the delay was shorter than it would have been for a red supergiant where light must traverse a much larger envelope. The neutrino detections from SN 1987A marked the birth of neutrino astronomy. For the first time, a celestial event had been studied not only through photons, but also through these elusive particles. It opened a new observational window on the universe, one that has since grown with the development of larger and more sensitive detectors, such as Super Kamiokande and IceCube. The lessons learned from 1987 continue to inform preparations for the next galactic supernova whenever it may occur. The importance of these detections was recognized immediately. Within days, scientific journals published reports detailing the neutrino bursts, and the connection to SN 1987A was established beyond doubt. The data became a cornerstone for supernova theory anchoring models of core collapse with direct evidence. It confirmed that the vast majority of the energy of a supernova is carried away by neutrinos, not by light or kinetic energy of the ejecta. The implications extended into particle physics as well. The travel time of the neutrinos from the Large Magellanic Cloud to Earth set limits on their mass. If neutrinos had significant mass, their speed would have been slightly less than the speed of light, leading to a measurable spread in arrival times. The narrow clustering of detections indicated that neutrinos must be extremely light, with masses no greater than a few tens of electron volts. This finding constrained theories of particle physics and cosmology, adding another dimension to the significance of SN 1987A. For many scientists, the neutrino detections were the most profound aspect of the entire event. While the light of the supernova dazzled the world, and the spectra revealed the chemistry of the explosion, the handful of neutrino signals represented a direct glimpse into the very heart of the star. They provided a silent, invisible confirmation that the core had collapsed, that neutrons had formed, and that the fundamental process of a core collapse supernova had occurred as theory had long suggested. In the decades since SN 1987A has remained the only supernova for which neutrinos have been detected. Its legacy continues to shape both astrophysics and particle physics, serving as a reminder of how even a few elusive particles can transform our understanding of the universe. As the first months passed after the discovery of SN 1987A, attention turned increasingly to the expanding shell of debris cast off by the explosion. The material ejected from the core collapse was hurled outward at immense speeds, carrying with it the elements synthesized in the progenitor star and in the explosion itself. Observations quickly confirmed that the ejecta were not a uniform sphere, but a complex and dynamic structure. Ground-based telescopes joined later by space observatories mapped the motion of this material as it raced outward into the surrounding interstellar medium. Early measurements of the ejecta velocity were striking. Spectroscopic lines, broadened and shifted by the Doppler effect, indicated that the fastest material was moving at more than 20,000 kilometers per second. This corresponds to a significant fraction of the speed of light, a testament to the energy released during the collapse. Slower layers followed behind, forming a stratified structure in which different elements occupied different shells. Hydrogen dominated the outermost regions, while oxygen, carbon and heavier elements filled the layers closer to the center. The geometry of the ejecta soon emerged as a central question. If the explosion had been perfectly spherical, the expanding shell would have appeared as a symmetric, uniformly bright feature. Instead, irregularities became apparent almost immediately. The light distribution varied with direction, and spectral lines hinted at clumps of material moving at different velocities. This suggested that the explosion itself had been asymmetric, with instabilities in the collapsing core creating jets or lobes that carried material outward unevenly. Polarimetric observations of the light confirmed this interpretation. Light from SN 1987A exhibited measurable polarization, which arises when the scattering environment is not symmetric. The degree of polarization changed over time, consistent with an evolving geometry that was not spherical. Such findings challenged earlier assumptions that core collapse supernovae could be modelled as simple radial explosions. Instead, the evidence from ATLAS 1987A demonstrated that turbulence convection and shock instabilities inside the core played significant roles in shaping the ejecta. Imaging in the optical range revealed the expanding debris as a diffuse cloud initially unresolved but gradually becoming more structured. As the years passed and telescopes such as the Hubble Space Telescope came online, the ejecta were resolved into intricate shapes. Filaments and knots appeared, some glowing brightly in emission lines of oxygen and hydrogen. These structures traced the uneven distribution of material and the shocks propagating through them. The ejecta expanded steadily, doubling in size every few years as it moved outward into the circumstellar medium. The expanding debris also carried within it the radioactive isotopes produced in the explosion. Gamma rays emitted by the decay of nickel and cobalt penetrated the surrounding gas, depositing energy that sustained the glow. Observations of gamma-ray lines provided direct evidence of these isotopes, confirming theoretical models of nucleosynthesis in supernovae. The amount of nickel produced, about half the mass of the Sun, was consistent with estimates from the light curve and spectra. This radioactive heating gradually diminished as the isotopes decayed, but for months it remained the dominant source of luminosity in the ejecta. As astronomers continued to monitor SN 1987A, they noticed that the expansion was not uniform even on large scales. Some regions of the ejecta appeared brighter than others, suggesting that certain clumps contained higher densities of material or more radioactive isotopes. High-resolution spectroscopy revealed velocity differences between these clumps, confirming that the explosion had mixed elements from deep inside the star with those from the outer layers. This mixing brought oxygen and heavier elements to the surface earlier than expected, altering the appearance of the spectra and providing insights into the physics of turbulent mixing in core collapse. Observations across multiple wavelengths added further detail. In the infrared, the ejecta glowed with thermal emission from dust and warm gas. This emission revealed the cooling process as the debris expanded and lost energy. In the ultraviolet, strong lines traced the ionized outer layers as they interacted with surrounding radiation. In the radio range, emissions from high-energy electrons spiraling in magnetic fields began to emerge, marking the early stages of a supernova remnant. Each wavelength added another layer of understanding to the complex portrait of the expanding ejecta. Over time, the ejecta also became increasingly transparent. In the early days, the dense gas was opaque, and light emerged primarily from the outer layers. As expansion thinned, the material photons from deeper regions could escape, revealing the inner structure. This evolution allowed astronomers to trace the stratification of elements and to test models of how the star had been assembled before its death. The visibility of deeper layers also confirmed that mixing had been extensive, with material from different fusion shells intermingled in ways not predicted by simple models. The geometry of the ejecta was further clarified by Doppler tomography, a technique that uses velocity information to reconstruct three-dimensional structures. By mapping how different spectral lines were shifted, astronomers created models of the spatial distribution of elements. These reconstructions showed that oxygen, for example, was concentrated in asymmetric clumps, while hydrogen remained more uniformly distributed. The resulting picture was of an explosion far more chaotic than the smooth shells often drawn in theoretical diagrams. The expanding ejecta of SN 1987A thus provided not only a spectacular display, but also a laboratory for studying the mechanics of stellar death. The velocities, asymmetries, and compositions recorded from its earlier stages continued to serve as benchmarks for simulations of core collapse. Every observation added constraints to models, forcing refinements in how physicists understand turbulence, neutrino transport, and shock propagation in the heart of a dying star. The story of the ejecta is also a story of enrichment. The elements it carried outward from carbon and oxygen to silicon and iron would eventually mix with the interstellar medium. Though diluted over thousands of years, they would become part of new stars' planets and perhaps even life. The observations of SN 1987A gave direct evidence of this process, showing how one star's death contributes to the ongoing chemical evolution of its galaxy. For astronomers, the expanding ejecta were a reminder that the brilliance of the supernova's light was only the most visible part of the event. Beneath the glow lay the mechanics of expansion, mixing and cooling processes that shape the long-term fate of the remnant. The shell of debris, once opaque and bright, would in time become transparent and faint, a ghostly reminder of the explosion. Yet, in those first years, as it rushed outward at tens of thousands of kilometers per second, it provided a clear and measurable signal of the immense forces unleashed in the final seconds of a star's life. Even decades later, the ejecta of SN 1987A continue to be observed. With modern telescopes, astronomers track its expansion, watch its knots and filaments evolve, and measure its emissions across the spectrum. Each new observation adds to the legacy of the event, building a continuous record of how a supernova remnant is born and grows. The expanding shell remains one of the most studied features of any stellar explosion, a dynamic laboratory unfolding in the skies above the southern hemisphere. In the years following the explosion of SN 1987A, astronomers began to notice not only the expanding shell of ejecta, but also a remarkable set of structures encircling the site of the supernova. These were the equatorial rings, three delicate arcs of gas arranged in a pattern that suggested a complex history of mass loss from the progenitor star. The central ring, nearly circular in appearance when viewed from Earth, lies in the plane of the progenitor's equator. Two larger rings arc above and below, forming a tilted hourglass shape when seen in projection. Together they became one of the most iconic features of the remnant, glowing first by reflected light, and later by direct interaction with the supernova's expanding shock waves. The equatorial ring spans about 1 light-year in diameter, with the two outer rings positioned roughly above and below the central plane. Their symmetry implies that Sanderleak -69202 underwent episodes of mass loss long before its collapse. At some point tens of thousands of years before the explosion, the star ejected material in a structured way shaping these rings. Why this occurred remains a subject of study, but the presence of such features provides a rare opportunity to examine the late evolutionary phases of a massive star. Initially, the rings were faint, visible only in narrow-band imaging that captured specific emission lines of ionized gas. They glowed because they had been illuminated by the flash of ultraviolet radiation released when the supernova occurred. This radiation ionized the gas, causing it to fluoresce for years afterward. Observations with the Hubble Space Telescope beginning in the early 1990s resolved the rings in detail, showing knots and clumps of denser material within them. These images became some of the most striking astronomical photographs of the era, revealing the beauty and complexity of the structures created by stellar winds. The geometry of the rings gave astronomers important information about the progenitor. Their alignment suggested that the star's mass loss had been shaped by rotation or by interactions with a possible companion star. One theory holds that Sanduleak 69202 may have been part of a binary system, and that gravitational effects during a merger or close interaction caused material to be expelled preferentially in the equatorial plane. Another possibility is that changes in the star's wind properties linked to shifts between blue supergiant and red supergiant phases produced the layered structures. Whatever the precise mechanism, the rings provided tangible evidence of the progenitor's unstable final stages. Over time, the equatorial ring evolved under the influence of the expanding ejecta. By the late 1990s, the fastest-moving material from the supernova had reached the inner edge of the ring. As the shock waves slammed into the denser knots of gas, they began to glow more brightly. Individual hotspots appeared around the circumference of the ring, each one a site where the shock front encountered clumps of material. These hotspots brightened steadily, becoming visible markers of the interaction between the ejecta and the circumstellar environment. The physics of these collisions is complex. The shock front compresses and heats the knots, driving their temperatures to millions of degrees and causing them to radiate across the electromagnetic spectrum. Optical telescopes record the glow of ionized atoms, while X-ray observatories detect the high-energy emissions from gas heated to extreme temperatures. As each knot is engulfed, it gradually fades, while new hotspots appear farther along the ring. This process has given astronomers a way to trace the expansion of the shock wave with remarkable precision. The outer rings located farther from the explosion site have remained largely unaffected by direct shocks, though they continue to glow faintly. Their origin is less clear than that of the equatorial ring, but they are thought to represent earlier episodes of mass loss from the progenitor. Together, the three rings form a coherent structure that speaks of a complicated and turbulent stellar history. Their persistence over decades has allowed astronomers to study the long-term evolution of circumstellar material shaped by massive stars. The chemical composition of the rings provides further insight. Spectroscopic studies show that the gas is enriched in nitrogen relative to hydrogen and helium, a sign that it was processed deep within the progenitor star before being expelled. This supports the idea that the rings were formed from material lost during advanced nuclear burning stages rather than from the general interstellar medium. The enrichment patterns also constrain the evolutionary path of Sanduleak 69202, suggesting that it underwent mixing processes that dredged up nuclear-processed material to its surface. Observations with the Hubble Space Telescope have been especially important in documenting the evolution of the equatorial ring. Images taken over years reveal the gradual progression of brightening hotspots, the fading of earlier ones, and the overall transformation of the structure as it interacts with the supernova's debris. These images, placed side by side, show the unfolding of astrophysical processes on timescales accessible within a human lifetime, something rarely possible in the study of stellar evolution. The ring system of SN 1987A also plays a crucial role in shaping the future remnant. As the ejecta continue to expand, they sweep up and interact with the circumstellar material, slowing in some directions and accelerating in others. This creates asymmetries in the remnant's growth, influencing the eventual structure of the supernova remnant that will persist for thousands of years. By studying these interactions in detail, astronomers gain insights not only into this single event, but into the general processes that govern the shaping of remnants throughout galaxies. The beauty and symmetry of the rings captured public imagination as well. They became emblematic images of SN 1987A, reproduced in scientific publications, educational materials, and even popular media. Their delicate glow, arranged in near-perfect alignment, contrasted with the violence of the explosion at their center, offering a striking reminder of the complex interplay between stability and chaos in the cosmos. For scientists, the equatorial rings remain a critical probe of the progenitor's past. By analyzing their structure, motion, and chemistry, researchers reconstruct the history of mass loss in the final tens of thousands of years before collapse. This information is otherwise inaccessible since direct observation of a star's internal evolution is impossible. The rings are thus a kind of fossil record, preserving in their shape and composition the conditions that preceded the supernova. Decades after the explosion, the rings continue to evolve. The shock wave has now illuminated much of the equatorial ring, and observations show that the process of brightening and fading is ongoing. Eventually, the shocks will pass through and disperse the ring, erasing its structure. But while it lasts, the system offers a rare, almost unique opportunity to watch the transformation of circumstellar material under the impact of a supernova. The triple ring system of SN 1987A stands as one of the defining features of the event, linking the death of a massive star to its turbulent history of mass loss. It is both a remnant of the past and a laboratory for the present, allowing astronomers to witness interactions that shape the birth of a new supernova remnant. In its symmetry and its glow, it holds the record of a star's unstable final acts, preserved in space for human eyes to study. When the expanding shock wave from SN 1987A reached the dense equatorial ring, the quiet glow of the structure transformed into a theatre of collisions. Each knot of gas within the ring became a point of sudden illumination, heated to extreme temperatures as the blast wave compressed and energized it. In the early years after the explosion, the ring appeared faint, lit only by the ultraviolet flash of the supernova. But by the mid-1990s, astronomers began to observe the appearance of distinct bright spots around the circumference. These hotspots marked the locations where the shock front struck the densest clumps. Over time, their numbers increased until nearly the entire ring was dotted with glowing regions. The physical processes at play are extreme. As the supersonic shock wave encountered the ring material, it generated pressures many thousands of times greater than those in the interstellar medium. Gas at the collision sites was compressed and heated to millions of degrees Celsius, radiating strongly in X-rays. Optical telescopes recorded the emission lines of ionized atoms glowing in hydrogen, nitrogen, and oxygen. The Chandra X-ray Observatory, launched in the late 1990s, provided high-resolution views of the high-energy radiation, revealing the progress of the shock as it advanced around the ring. The sequence of events unfolded over decades, allowing astronomers to watch in near real time the transformation of circumstellar material under the force of a supernova blast. The first hotspots to appear grew steadily brighter, reaching peak luminosities before eventually fading as the shock passed through and the gas cooled. New hotspots continued to emerge farther along the ring, each one a marker of progress. The pattern resembled a wave of illumination moving around the circumference, though in reality it was the physical passage of the shock front. By mapping these appearances, astronomers could measure the speed and structure of the expanding blast. Spectroscopic measurements added crucial details. The emission lines from the hotspots carried information about velocity and density. Broadening of the lines indicated turbulence and high speeds, while the ratios of line strengths revealed temperatures and chemical abundances. These data confirmed that the material in the ring had been enriched by nuclear processing within the progenitor star. The high levels of nitrogen in particular pointed to material expelled during late evolutionary stages long before the final collapse. The interaction also revealed the clumpiness of the ring. Rather than being a smooth torus, the ring contained knots and irregular densities. Each knot responded differently to the shock, some producing intense but short-lived flares, others glowing more steadily over years. This variability provided a window into the structure of the circumstellar medium, shaped by the winds and outflows of the progenitor star in its unstable final tens of thousands of years. In the X-ray regime, the collision created a steadily brightening signal. As more of the ring became engulfed by the shock, the total X-ray luminosity rose. Chandra observations showed the emergence of an expanding X-ray shell, marking the growing volume of shocked gas. The spectrum of the X-rays indicated temperatures of tens of millions of degrees, consistent with shock velocities of thousands of kilometers per second. These measurements allowed astronomers to test models of shock physics under conditions impossible to reproduce on Earth. Radio observations also recorded the interaction. As the shock accelerated particles to near the speed of light, they produced synchrotron radiation visible in radio wavelengths. Arrays such as the Australia Telescope Compact Array trace the growth of radio emission, mapping the sites where magnetic fields and energetic electrons interacted. The combination of radio-optical and X-ray data provided a multi-wavelength portrait of the collision, each wavelength highlighting a different aspect of the same process. The impact of the shock wave on the equatorial ring has broader implications for the future of the remnant. As the blast continues to sweep through the ring, it transfers momentum and energy, dispersing the material outward. Over time, the ring will be destroyed, its gas mixed with the expanding ejecta. This process will enrich the supernova remnant with heavy elements and alter its geometry. The illuminated hotspots represent a transient phase in this transformation, visible only for decades before fading into the larger remnant. Observations of the hotspots have also allowed astronomers to refine the distance to the Large Magellanic Cloud. By measuring the angular size of the ring and comparing it with the time delays in light travel from different points around the ring, astronomers derived geometric distances. These measurements, combined with other methods, provided one of the most accurate estimates of the distance to SN 1987A, and thus to the Large Magellanic Cloud itself. Such calibrations are critical for the cosmic distance ladder, the framework used to measure distances across the universe. The unfolding of the shock ring interaction offered a rare opportunity to study astrophysical processes in a time frame comparable to a human career. Normally, the evolution of supernova remnants occurs over centuries or millennia, far too slowly to observe significant changes. In the case of SN 1987A, however, the nearby distance and dense ring material compressed this timescale, producing visible transformations within years and decades. This made it possible to track shock physics, chemical enrichment, and remnant formation in ways not possible with older, more distant supernova remnants. Each new observation added detail to the story. Hubble images showed the glowing knots, their brightness waxing and waning as the shock passed. Chandra data revealed a steady increase in X-ray brightness, with subtle shifts indicating changes in temperature and density. Radio arrays mapped the expansion of synchrotron emission, tracing magnetic fields energized by the collision. Together, these records created one of the most complete multi-wavelength portraits of shock interactions ever obtained. The significance of these observations extends beyond SN 1987A. They provide a reference for understanding how supernovae shape their environments in general. When massive stars explode, they do not do so in empty space, but in regions filled with material shed during their lifetimes. The collisions between ejecta and circumstellar matter are fundamental to the structure and chemistry of galaxies influencing star formation and the distribution of elements. SN 1987A, with its equatorial ring, offers the clearest and most detailed example of this process. The continuing interaction between the shock and the ring ensures that SN 1987A remains a living laboratory for astrophysics. Each passing year brings new data as fresh knots ignite and older ones fade. Eventually, the entire ring will be overtaken, leaving behind a remnant shaped by the collision. But for now, the glowing arcs and bright spots continue to tell the story of how a star's death reshapes its immediate surroundings. The ring, once a relic of the progenitor's unstable winds, has become the canvas upon which the dynamics of a supernova are painted visible to telescopes around the world. In this way, the equatorial ring is not merely a backdrop to the supernova, but a central player in its continuing evolution. The collision of shock waves with this dense structure has provided a unique view into processes otherwise hidden by distance or timescale. For scientists and observers, it remains one of the most captivating aspects of SN 1987, a reminder that the death of a star is not a single event, but a cascade of transformations unfolding across decades. As the debris of SN 1987A continued to expand and interact with the equatorial ring, astronomers turned their attention to an equally intriguing development inside the cooling ejecta, the formation of dust. In the months after the explosion, the supernova's light curve and spectra showed evidence of molecules forming in the rapidly cooling gas. By the end of 1987, infrared telescopes began to detect excess emission that could not be explained solely by hot gas. This signal suggested that solid particles were beginning to condense from the heavy elements synthesized in the star and in the explosion. Dust is a crucial product of supernovae. These microscopic grains of carbon silicates and other compounds are the raw material from which future planets, comets, and even the building blocks of life can eventually arise. Detecting their formation in real time within SN 1987A gave astronomers a rare opportunity to watch one of the universe's essential processes unfold. The first clear evidence came from observations of carbon monoxide molecules detected by their infrared spectral signatures. These molecules form efficiently in cooling gas and act as precursors to dust grains. Their presence indicated that conditions inside the ejecta had reached temperatures low enough for chemical bonds to survive. Soon afterward, infrared measurements revealed emission consistent with newly formed dust. Initially, the amount appeared modest, suggesting only a small fraction of a solar mass of dust grains. For many years, the dust yield of SN 1987A was thought to be relatively low. However, as observational technology improved, particularly with the advent of space-based infrared observatories such as the Spitzer Space Telescope and later the Herschel Space Observatory, the picture changed dramatically. These instruments, operating at longer wavelengths capable of detecting cold dust, revealed that far more material had condensed than previously believed. By the early 21st century, estimates indicated that SN 1987A had produced between half and one solar mass of dust, making it one of the most significant stellar sources of dust known. The formation of dust in such large quantities challenged earlier assumptions. Before SN 1987A, many astronomers doubted whether supernovae could be efficient dust producers because the harsh radiation and shocks from the explosion might destroy grains as quickly as they formed. The observations from SN 1987A showed that dust formation not only occurred, but did so robustly, suggesting that supernovae may play a major role in enriching galaxies with dust. This has implications far beyond the Large Magellanic Cloud. In the early universe, where galaxies formed rapidly and massive stars died quickly, supernovae may have been the dominant source of dust. Observing SEN 1987A provided a nearby laboratory for testing these ideas linking local processes to cosmic history. The dust grains themselves are diverse. Models and spectra suggest the presence of silicate grains, carbonaceous particles, and potentially iron-rich compounds. Their sizes range from nanometers to micrometers, with larger grains more likely to survive the shocks and radiation that follow. As the ejecta continue to expand and interact with the equatorial ring, some of these grains will be destroyed, but others will endure, eventually mixing into the interstellar medium. The chemistry of the dust also provides insight into the internal mixing of the ejecta. The detection of molecules such as silicon monoxide and carbon monoxide in the same regions implies that different fusion products from the progenitor star were mixed during the explosion. This mixing allowed elements that had been separated into different layers before collapse to combine chemically afterward, producing a wider variety of dust species. Infrared and submillimeter observations by the Atacama Large Millimeter-Submillimeter Array ALMA added further clarity. ALMA resolved the central ejecta of SN 1987A and directly imaged the cold dust inside. These observations revealed clumps of material rich in dust with masses far higher than earlier estimates. The cold temperatures, only tens of degrees above absolute zero, showed that the dust had cooled significantly in the decades since the explosion. ALMA's ability to trace specific molecules also confirmed the presence of carbon monoxide and silicon monoxide in large quantities, linking the chemistry of the gas to the solid grains condensing within it. The dust formation in SN 1987A also affected the appearance of the supernova. As grains condensed, they absorbed visible light and re-emitted it in the infrared. This caused the optical brightness to decline more rapidly in some wavelengths than expected, while the infrared emission increased. These changes provided indirect evidence of dust formation even before the grains were directly observed. In later years, as the ejecta became more transparent, the influence of dust on the observed spectra became even more pronounced, blocking light from some regions while allowing emission from others. The survival of dust in the hostile environment of a supernova remnant remains an open question. Shock waves travelling through the ejecta can heat and sputter, grains destroying many of them. Yet the observations of SN 1987A suggest that a substantial fraction has survived. If even part of the mass detected by ALMA endures, as the remnant evolves, it will contribute significantly to the dust budget of the Large Magellanic Cloud. This makes SN 1987A a key case study for understanding how galaxies maintain and recycle their dust content. The link between dust formation and cosmic evolution is profound. Dust grains are essential for cooling interstellar gas, allowing new stars to form. They provide surfaces on which molecules such as water and complex organics can assemble. They shape the appearance of galaxies by absorbing ultraviolet and visible light and re-radiating it in the infrared. Without dust, the cycle of star and planet formation would be very different. By confirming that supernovae can produce large amounts of dust, SN 1987A has illuminated one of the pathways by which galaxies evolve chemically and structurally. For astronomers, watching the dust form inside SN 1987A has been like witnessing the raw materials of future worlds being created. The star's death scattered into space not only light and energy, but also solid particles that may one day become part of planets' moons or comets in distant star systems. The process is invisible to the naked eye, but in the infrared it shines clearly, telling a story of transformation from hot gas to solid grains. Decades after the initial explosion, the study of dust in SN 1987A continues. Instruments on the James Webb Space Telescope now add further detail with unprecedented sensitivity in the mid-infrared. These observations reveal both the distribution and composition of the grains, refining estimates of their total mass and diversity. Each new study deepens the understanding of how dust forms and survives in one of the most violent environments in the cosmos. The dust of SN 1987A is both an end and a beginning. It is the end of a star's long nuclear journey, the final condensation of elements forged over millions of years. But it is also the beginning of new cycles, as those grains, if they survive, will join the interstellar medium where gravity may one day gather them into new systems. In this way, the formation of dust within the remnants of SN 1987A bridges the death of one star to the future of many others, a quiet but profound transformation still unfolding in the depth of space. As SN 1987A aged beyond its initial brilliance, astronomers began to observe the rise of high-energy emissions, especially in the X-ray and gamma-ray bands. These emissions provided crucial insights into the heating of the remnant and the acceleration of particles within it. When the blast wave struck the dense equatorial ring, the collisions produced shocks that heated the gas to temperatures of tens of millions of degrees Celsius. At such extremes, the gas radiates primarily in X-rays. Instruments aboard satellites, particularly the Chandra X-ray Observatory and XMM Newton, recorded the steady brightening of the supernova remnant in these wavelengths. The X-ray light grew stronger year after year, a sign that the shock was ploughing into more and more dense material. Chandra's sharp imaging allowed astronomers to map the emission across the ring. The hotspots visible in optical light glowed even more fiercely in X-rays, each one a site of intense heating. Over time, the X-ray emissions spread around the entire circumference, tracing the advance of the shock front. The energy released was immense, a continuing conversion of kinetic energy from the expanding ejector into thermal energy of the circumstellar gas. These observations offered a direct look at the physics of strong shocks in astrophysical settings. The temperatures implied by the X-ray spectra, tens of millions of degrees, could not be produced in ordinary stellar environments. They confirmed that the expanding blast of SN 1987A had reached a new phase, transitioning from a luminous stellar explosion to a young supernova remnant dominated by high-energy processes. The X-ray data also revealed the chemical composition of the shocked gas. Lines from highly ionized oxygen, neon magnesium, and silicon appeared in the spectra, each a tracer of the elements created in the progenitor and expelled during the explosion. The intensities and ratios of these lines allowed astronomers to estimate abundances and to confirm that the gas in the ring had been enriched by stellar nucleosynthesis. These measurements provided another line of evidence that massive stars like Sandelik 69202 play a central role in enriching galaxies with heavy elements. Alongside the X-rays, gamma-ray observations captured the decay of radioactive isotopes produced in the explosion. In particular, lines from the decay of cobalt-56 were detected in the months after the explosion, confirming theoretical predictions that radioactive decay powers the later phases of the light curve. The detection of gamma rays was possible only because SN 1987A was so nearby. For most supernova in distant galaxies, such signals are too faint. In this case, they offered a rare window into the nuclear processes at the heart of the explosion. The high-energy emission from SN 1987A was not limited to thermal radiation from hot gas. Non-thermal processes also played a role. As the shock waves accelerated charged particles to near-relativistic speeds, they produced synchrotron radiation visible in both the radio and X-ray bands. This emission provided direct evidence that supernova remnants are sites of cosmic ray acceleration, a phenomenon long suspected but difficult to prove. The case of SN 1987A strengthened the link between supernovae and the high-energy particles that pervade the galaxy. The X-ray brightening of the remnant followed a clear trend. From the late 1990s onward, the luminosity rose steadily as the blast wave swept through more of the dense ring. By the early 2000s, the emission was several times stronger than it had been in the first decade. Each hotspot contributed to the growing total, and as they merged into a continuous arc, the remnant shone as one of the brightest X-ray sources in the Large Magellanic Cloud. The detailed monitoring by Chandra provided a moving picture of this transformation, with images taken years apart showing the growth of the X-ray shell. The rise of X-rays also affected the appearance of the remnant in other wavelengths. As gas was heated and ionized, it emitted in optical lines, producing bright knots visible in Hubble images. The combination of optical and X-ray data allowed astronomers to link the microscopic physics of shocks to the macroscopic evolution of the remnant. The alignment of features across wavelengths confirmed that the same collisions driving X-ray emission were also responsible for the glowing hotspots seen in visible light. The particle acceleration processes in SN 1987A have become a major area of study. When shocks accelerate electrons, they emit synchrotron radiation in radio waves and X-rays. These electrons may also collide with photons, boosting them to even higher energies, in a process known as inverse Compton scattering. The observations of SN 1987A suggest that both mechanisms are at work. The efficiency of acceleration is remarkable, showing that supernova shocks can convert a significant fraction of kinetic energy into energetic particles. This efficiency supports the idea that supernovae throughout galaxies are the primary source of cosmic rays. The monitoring of SN 1987A has also revealed changes in the balance of emissions over time. As the shock consumed more of the ring, the X-ray emission began to plateau and even decline in some energy bands, suggesting that the densest parts of the ring had been traversed. Meanwhile, emission from the interior, where the ejecta themselves were interacting with slower-moving material, began to emerge. These transitions mark the evolution from the phase dominated by circumstellar collisions to one where the remnant as a whole began to glow in X-rays. Another remarkable feature of the high-energy data is the evidence of asymmetry. Some regions of the ring brightened earlier or more intensely than others, indicating that the density of the circumstellar gas is not uniform. These variations provide valuable information about the progenitor's mass loss history. They show that Sanderleak 69202 did not shed its outer layers in a simple smooth wind, but in a more complicated pattern, producing knots and arcs that later shaped the remnant's evolution. In the broader astrophysical context, the high-energy emissions of SN 1987A have confirmed that supernova remnants are laboratories for extreme physics. They demonstrate how shock waves heat gas to millions of degrees, how nuclear decay sustains luminosity, and how particles are accelerated to energies far beyond those achievable on Earth. Each observation of X-rays and gamma rays has tied theoretical models to real processes, making SN 1987A a cornerstone of high-energy astrophysics. The continuing monitoring of SN 1987A in X-rays ensures that the story is not finished. Decades after the explosion, new data are still being gathered, tracing how the remnant evolves as shocks move beyond the equatorial ring and into the surrounding medium. Future observatories with greater sensitivity and resolution will extend this record, capturing even fainter emissions and finer details. For now, the rise of X-ray and gamma-ray light from SN 1987A remains one of the defining chapters in the history of the event, a phase that revealed the immense energies unleashed when a star dies, and the remarkable processes that shape the aftermath of such explosions. From the moment SN 1987A was identified as a core collapse supernova, astronomers expected that the explosion would have left behind a compact remnant at its core. In theory, the collapse of the iron core of Sanduleak-69202 should have produced either a neutron star or, if the mass were great enough, a black hole. For decades, the search for this hidden remnant has been one of the central pursuits in the study of SN 1987A. Yet despite intensive observation across all wavelengths, the compact object has remained elusive. In the first weeks after the explosion, the intense luminosity of the ejecta made it impossible to see deep into the center. The brilliant light of the expanding debris outshone any compact remnant that might have formed. As the supernova faded over months and years, astronomers began to look more carefully for telltale signs. A newly formed neutron star would likely emit in X-rays and perhaps in radio pulses like the pulsars seen in other remnants. A black hole would be far more difficult to detect directly, though accretion of fallback material could in principle produce radiation. The earlier searches using radio and X-ray telescopes yielded no clear detections. Upper limits on emission were established, suggesting that if a neutron star were present, it must be faint or obscured. Some theorists proposed that much of the ejecta remained too dense, absorbing and scattering any radiation from within. Others suggested that if the remnant were a black hole, it might emit little or nothing at all. As years passed, astronomers continued to probe the center of the remnant with increasingly sensitive instruments. The Hubble Space Telescope provided high-resolution optical images, but no point source emerged. The Chandra X-ray Observatory searched for localized emissions, but the brightening of the equatorial ring and the diffuse X-ray glow made it difficult to distinguish a central compact object. Radio telescopes also failed to reveal pulsations. Still indirect clues began to appear. Observations with the Atacama Large Sub-Millimeter Array detected warm dust in the central regions of the remnant heated to temperatures higher than expected by radioactive decay alone. This raised the possibility that an unseen source of energy, perhaps a young neutron star, was contributing to the heating. In 2019, analysis of ALMA data suggested the presence of a compact object embedded within the dense dust, its radiation reprocessed into infrared wavelengths. If confirmed, this would represent the first evidence for the long-sought remnant. The difficulty lies in the opacity of the ejecta. Even decades after the explosion, the central regions remain enshrouded in thick clouds of dust and gas blocking direct optical and X-ray views. The compact object, if present, may be invisible until the debris thins further or until its emission can be detected in wavelengths less affected by dust. This challenge has kept the search ongoing, with each new generation of telescopes bringing the possibility of success. The physics of core collapse suggests that a neutron star is the most likely outcome. The mass of Sanduleak-69202 was sufficient to produce a compact core, but probably not great enough to form a black hole immediately. In this scenario, the remnant should be a hot, rapidly spinning neutron star, perhaps with a strong magnetic field. If so, it might resemble a young pulsar emitting beams of radiation as it rotates. Yet no pulses have been detected, raising the possibility that its beam does not sweep across Earth, or that it is hidden by intervening material. Another possibility is that the neutron star is covered by fallback material. After the explosion, some fraction of the ejecta may have lacked the velocity to escape, and could have fallen back onto the remnant. This accretion could smother the neutron star, altering its emission and making it difficult to detect. Alternatively, if enough fallback occurred, it could have driven the remnant into collapse, forming a black hole. Distinguishing between these scenarios is one of the major challenges in interpreting the absence of direct evidence. The potential detection in ALMA data has reignited interest. The excess thermal emission in the central ejector appears consistent with heating from a compact source, and some models suggest that a neutron star shining primarily in the infrared could fit the observations. However, alternative explanations remain possible, such as radioactive heating by longer-lived isotopes. Further data from instruments like the James Webb Space Telescope may help to resolve the ambiguity with its ability to probe infrared emission through dust with unprecedented sensitivity. The search for the compact remnant of SN 1987A is not merely a curiosity. It carries profound implications for astrophysics. If a neutron star is confirmed, it would provide a rare opportunity to study such an object at its very birth, only decades after its formation. Observations could reveal how neutron stars cool, how their magnetic fields evolve, and whether they produce winds or jets that shape the surrounding remnant. If instead the remnant is a black hole, it would provide the first direct evidence of black hole formation in a nearby supernova, offering new insights into the thresholds between neutron star and black hole outcomes. For now, the central compact object of SN 1987A remains hidden, its nature inferred but not proven. Each new observation pushes the limits of detection, searching for a faint point of light, a pulse of radiation, or a subtle excess of energy that could reveal its presence. Decades after the explosion, the hunt continues, with astronomers watching closely for the moment when the veil of dust finally lifts, or when a new instrument catches the remnant's elusive signal. The mystery of the missing core has become one of the defining features of SN 1987A, reminding astronomers that even in the best-studied supernova, some of the most important answers remain concealed. The expanding rings and glowing hotspots tell of the interaction between debris and environment, but at the heart of the remnant lies the unanswered question of what exactly was left behind when the core of Sanderlic-69202 collapsed. Whether neutron star or black hole, the compact remnant embodies the ultimate fate of massive stars, a final transformation hidden for now but destined to emerge as the remnant evolves. More than 3 decades after its appearance, SN 1987A remains one of the most intensively studied astronomical objects in the sky. The remnant has transformed from a single point of blinding brilliance into a complex structure of expanding ejecta, glowing rings, and energetic shocks. Astronomers continue to monitor it across all wavelengths, each new observation adding to the story of how a massive star dies and how its death reshapes its surroundings. The present state of SN 1987A shows the aftermath of this evolution in remarkable clarity. In optical light images from the Hubble Space Telescope reveal the familiar equatorial ring now lit by numerous hotspots, created where the shock wave collides with dense knots of gas. The ring is brighter and more intricate than it was in the early years, though some regions have already begun to fade as the shocks pass through and disperse the material. Beyond the ring, the expanding ejecta glow faintly still visible in emission lines of hydrogen, oxygen, and other elements. These filaments trace the motion of the debris as it continues to expand outward at thousands of kilometers per second, gradually blending into the interstellar medium of the Large Magellanic Cloud. In X-rays, observations by Chandra show a bright shell of emission encircling the remnant. The gas, heated to tens of millions of degrees by the shocks, radiates strongly, making SN 1987A one of the brightest X-ray sources in its galaxy. The shell is asymmetric, with some regions brighter than others, reflecting variations in the density of the circumstellar medium. These asymmetries continue to provide clues about the mass loss history of the progenitor star in the tens of thousands of years before it exploded. The X-ray emission has peaked in some energy bands and begun to level off, indicating that the shock is moving beyond the densest parts of the equatorial ring. This transition marks the gradual end of the phase dominated by collisions with the ring, as the remnant enters a new stage of expansion into the surrounding interstellar medium. In the infrared observations from the James Webb Space Telescope and ALMA provide a view of the dust within the remnant. These instruments reveal large masses of cold dust in the central ejecta, amounting to nearly a solar mass. The dust is clumpy and unevenly distributed, with some regions more enriched than others. Its survival in the harsh environment of a supernova remnant confirms that supernovae are efficient producers of dust, a finding with broad implications for the evolution of galaxies and the early universe. The infrared view also suggests that a compact object may be hidden within heating some of the dust from the inside. Radio observations continue to track synchrotron emission from particles accelerated by the shocks, arrays such as the Australia Telescope Compact Array Map. The remnant in detail showing how the expanding blast wave energizes electrons and amplifies magnetic fields. The radio emission complements the X-ray and optical views together, forming a complete picture of the energetic processes underway. The radio data confirm that SN 1987 is a site of cosmic ray acceleration, a role expected for supernova remnants, but rarely observed so directly. The search for the compact remnant remains one of the most compelling aspects of current study. Hints from ALMA and other instruments suggest that a neutron star may indeed be present, hidden by dust and gas. If so, its emergence in the coming decades could provide an unprecedented opportunity to observe a neutron star only a few decades after its birth. Confirmation would link theory and observation in a way not possible with older remnants, allowing astronomers to study how such objects evolve from their earlier stages. If instead the remnant is a black hole, it will demonstrate that stellar mass black holes can form directly in supernova explosions, an outcome that has not yet been confirmed in a nearby case. Either possibility underscores the continuing importance of monitoring the center of the remnant. The present state of SN 1987A also highlights its role as a cosmic laboratory. The equatorial ring continues to serve as a natural experiment in shock physics as the blast wave strikes one clump after another. The ejecta provide insights into mixing nucleosynthesis and dust formation. The high-energy emissions demonstrate how shocks accelerate particles and heat gas. Each of these processes is relevant not only to this one event, but to supernovae across the universe. The lessons learned from SN 1987A have reshaped models of core collapse of circumstellar interaction and of galactic chemical evolution. Decades of continuous monitoring have made it a benchmark for astrophysical research. Few objects in the sky are as thoroughly documented. Its light curve spectra images and particle detections form one of the richest datasets in the history of astronomy. These records continue to be used to refine simulations and to test new theories. For astronomers, SN 1987A is not merely a relic of a single star's death, but a reference point for understanding the broader population of supernovae. The present state of SN 1987A is one of transition. It is no longer the brilliant star-like point that astonished observers in 1987, nor is it yet the faint diffuse nebula that it will become in centuries to come. Instead, it is a dynamic and evolving remnant, bright in X-rays, structured in optical light, rich in dust in the infrared and glowing in radio waves. Its complexity reflects the many processes at play, expansion collision, mixing, cooling and acceleration. For now, it remains one of the most closely observed objects in the sky, a supernova remnant in the making, still teaching lessons more than 30 years after the night when its light first reached Earth. The story of SN 1987A continues, written each year by telescopes around the world and above the atmosphere. It will remain visible and active for centuries, evolving slowly into a classic supernova remnant. For this generation of astronomers, however, it is a unique opportunity to watch the transformation unfold in real time. The present state of SN 1987A is both a culmination of decades of study and a prelude to discoveries yet to come, a vivid reminder of how a single star's end can illuminate the workings of the universe.